today we're going to talk about logarithmic functions. In our previous lesson, we talked about exponential functions, and we saw that all of our exponential functions have inverses. So if we were trying to find the inverse of an exponential function like y equals b to the x, our first step would be to switch x and y. And then we want to solve for y, and that gives us our inverse. Now, if I look at this expression, I've got b to the y. So how do I undo that exponent? Sometimes I hear students say, well, can we just divide by b? And no, we can't do that because b and y are not being multiplied. So that doesn't work. Then we think about how would we undo something that was squared? We'd take the square root. Since this has a power of y, we think about, okay, well, let's take the yth root of both sides. But even that, although that gets b by itself, it doesn't get y by itself. So now we're still stuck with this expression that x equals b to the y, and I want to know, how do I solve for that exponent? The answer to that is using logarithms. Logarithms are what we use to solve for an exponent, or in other words, to isolate an exponent, get that exponent all by itself. Essentially, when we think about inverses, they're undoing that exponential relationship. The logarithmic function is the inverse of an exponential function. We can write it in function notation, f of x equals log base b of x, that's how we read that, or as an equation, y equals log base b of x. Now it has the same restrictions on b that we had for our exponential functions, so b must be greater than 0, b cannot equal 1. And now we have a new restriction that x must be greater than or equal to 0. And that comes from that inverse relationship between our exponential functions and our logarithmic functions. And we're going to look at that in just a second when we start talking about all the characteristics of our log functions. But it is important to remember that x must be greater than 0, and then we still maintain those restrictions on our base. Basically, if we're using a log to isolate our exponent, then y equals log base b of x is equivalent to x equals b to the y. That previous equation that we had where we were solving or trying to solve for that exponent, these two are equivalent, which means they say the same thing, they're just represented differently. So we're going to look at converting back and forth between logarithmic expressions and exponential expressions. Let's rewrite what we just had, the equivalent statements. Y equals log base b of x is equivalent to x equals b to the y. Now, we're going to start by converting from log to exponentials, and that's actually much easier. We can use a kind of a little path, a visual guide to get us to that different form. And what that is, it looks kind of like a swirl, or I've heard students call it a tornado. We're going to start with our base. We're going to raise it to a power of 3, and we're going to set it equal to our argument. So if I take this logarithmic equation and I want to write it in exponential form, it is 7 cubed equals x. 7 cubed equals x. Trying another one, again using that same tornado pattern. We start with our base, we raise it to this power, and then we're going to set it equal to our argument. So we have b squared equals 16. Now I don't want you to solve this, although we can kind of think about what values of b we could have. But in this, we're just asking you to write it as an exponential, so you want to leave it as b squared equals 16. But let's think about this. If you were to solve this equation, which we're going to do eventually, if we were to solve b squared equals 16 here, what would we get for b? Well, we know we need to take the square root of both sides, and when we take the square root of both sides, we typically add our plus or minus, so we get b is equal to 4 and negative 4. But with an exponential, or excuse me, a logarithmic equation, we end up with the possibility of arriving at an extraneous solution, which is a solution that doesn't actually work for your original function or your original equation. So if I look at this, I got b is equal to 4 or negative 4. Let's look back at the original. Notice where b is. B is the base of this logarithm, and what are our restrictions on our base? Our base must be greater than 0, and our base cannot equal 1. Is negative 4 greater than 0? Nope. So our only solution, if we were asking you to solve it, would be b equals 4. Again, at this point in time, we're not asking you to solve these equations, but I'm trying to get you guys thinking ahead because eventually we are going to be solving logarithmic and exponential equations. Log base 4 of 26 equals y. We start with our base, we raise it to a power of y, and set it equal to 26. So 4 to the power of y equals 26. So it's pretty straightforward to convert from a logarithmic expression to an exponential expression. Now we're going to go the reverse route. We're going to start with an exponential and convert to a logarithmic expression or equation. So I like to think about what we use a log for. We use a log to isolate the exponent. That looks like isolate. So in this expression, what's going to end up being by itself? Our exponent is what's going to be by itself. Now, when we convert to a log, we've got log, and then we've got a specific base. If you remember that equivalent statement, the base of our exponential is equal to the base of our logarithm. So what's the base of my exponential equation? It is 2. And now there's only one thing left. I need the argument for my log, and the only piece that I haven't used for my exponential equation is y. So it's 5 equals log base 2 of y. Now this is really easy to check when we're done. If we have 5 equals log base 2 of y, I can use that tornado pattern to get myself back to the exponential to double check that I've set it up correctly. So 2 to the 5th equals y. That matches what I originally had, so I'm good to go. B cubed equals 27. Converting to a log or using a logarithm isolates the exponent. So 3 is going to be by itself. The base of my logarithm is the same as the base of my exponential. So we have a base of b, and we fill in what's left, 27. E squared equals x. We're isolating the exponent, so 2 is by itself. The base of my exponential is the base of my logarithm, so we have a base of e, and what's left becomes my argument. Just to review, e is that natural number that we learned about in our previous lesson. It's approximately equal to 2.71828, and we have a button on our calculator that will evaluate e so that we don't have to use an approximation. It's very similar to pi that we've seen in geometry classes. So now we want to try evaluating a logarithm without using our calculator. We're going to talk about in a second the restrictions that our calculator has. So we want to try just using the definition of a logarithm to see if we can evaluate one. With a logarithm, we are solving for the exponent. It helps us figure out what the exponent is, the missing exponent. So if I've got log base 10 of 100, what this is asking is 10 to what power equals 100? Well, that power is 2. So log base 10 of 100 is equal to 2. Log base 5 of 1 over 125. We're trying to figure out 5 to what power equals 1 over 125. Well, we see that 125 in the denominator. Hopefully we're thinking about a negative exponent. And 5 cubed is 125, so 5 to the negative third power equals 1 over 125. Or log base 5 of 1 over 125 equals negative 3. Log base 36 of 6. Again, 36 to what power equals 6? Well, the relationship between the 6 and the 36 is a square or a square root relationship. But I got to figure out what power do I want to raise 36 to in order for it to take the square root. Because I'm not squaring this, 36 squared is certainly not 6. So if I remember, the square root of x is equal to x to the 1/2. So if I want to take the square root of 36, this is 36 to the 1/2 power, and that is equal to 6. So 1/2 is equal to log base 36 of 6. To just review a little bit more with this conversion between an exponent and a radical, if I have the nth root of x to the m, this is the same as x to the m over n. The index of your radical becomes the denominator of your rational exponent. Any exponent that's on the radicand becomes the numerator of your rational exponent. So we can see that with this concrete example of the square root of x. The index here is 2. Even though we don't write it, we know that the index is 2 for a square root. And the exponent on x is 1, so that's how we got a power of 1/2 for this one. Log base 4 of the 5th root of 4. 4 to what power is equal to the 5th root of 4? Well, on this side over here, I can convert the 5th root of 4 to an exponent. That's the same as 4 to a power of 1/5. So now I'm just trying to figure out 4 to what exponent equals 4 to the 1/5. Well, that exponent is clearly 1/5. And that's equal to log base 4 of the 5th root of 4. So now that we know how to evaluate logarithms, let's look at some properties of logarithms. Again, reviewing those, the restrictions on our base, b must be greater than 0, it must be positive, and b cannot equal 1. The inverse properties of our logarithms: log base b of b to the x is equal to x, and b raised to the power of log base b of x is equal to x. Now what we're looking at here is actually some composite functions. This is a log equation with an exponential on the inside. This one is an exponential equation with a log on the inside. So we're going to investigate the proof of this, and it's going to review some of those properties of inverses that we saw back in Unit 2. So we've got f of x and we've got g of x. F of x is a log equation. G of x is an exponential. Now, we know that f of x and g of x are inverses. That we know because exponentials and logarithms are inverses. We're going to just take that to be true. Now, we also know that if you take the composite of two functions that are inverses, then it will simplify to x. So f of g of x is equal to x, or g of f of x is equal to x. And if that's true, then they're inverses. So we already know that these two are inverses. So what happens when we combine them, when we make the composite function? F of g of x is the same as f of g of x, written in function notation. If I substitute g of x is b to the x. Now this is function notation telling me to substitute b of x everywhere I see an x in f. So this is log base b. Instead of x, like we have here, we're going to substitute b to the x. So this is the composite function f of g of x. Because I know that f of x and g of x are equal, that means that this is equal to x, which is one of those inverse properties we just saw. Now we can go the reverse, where we find g of f of x First, we're going to substitute f of x, so that is log base b of x. And now this is the function notation telling me to plug in log base b of x everywhere I see an x in g. So what does that look like? That looks like b raised to the log base b of x. Again, since I already know that f of x and g of x are inverses, then this must equal x. And these are the two rules we just wrote down on that previous page. Now, this seems like a lot of work, but in reality, it speeds up problems quite nicely. If I see a problem that looks like this, log base 7 of 7 to the 8th, because our base of the log is the same as the base of my exponential, the inverses cancel each other out, so we're left with just 8. Okay, just comparing this to the rule that we had log base b of b to the x. This is equal to x. So in this example, my b's are 7s and my x is my 8. Same thing down here. 3 raised to the log base 3 of 17. Because my bases are the same, this is equal to 17. Now, there are other ways of getting to the solution of 8 and 17, and the more you start learning and working with logarithms and exponential expressions, you guys might find different ways of getting to this, but the inverse properties are pretty common and we use them a lot, so it's nice rules to have memorized. So now let's talk about the graphs of a logarithmic function. Again, relating back to an exponential function, because they're inverses of one another, it tells us so much about the two functions. Exponential and logarithmic functions are inverses, so what does that tell us about the graph? If you remember from our lesson on inverses, that tells us that the graphs are reflections about the line y equals x. Now that also helps us in identifying how we're going to graph logarithmic functions. We've already graphed exponential functions. We've seen how to use our calculator. What we're going to talk about next is that our calculators can't evaluate logarithms all the time. So we're in trouble when we're trying to pick x values and plug them into a log function. But if I can evaluate an exponential function and graph that, I know to graph the inverse, I just switch your x and your y coordinates. Now this is going to be the technique that I show you guys in class. Again, if you're thinking critically and really learning this concepts, you might discover that there are some other ways to graph. And obviously, if you discover them and you want to run them by me during office hours or during class, please be my guest. I want to make sure that you're on the right track with these discoveries. But this is how we're going to graph a logarithmic function, just by finding the inverse, making a table of values, and switching our x and y coordinates. So we're going to start by graphing two functions that are inverses, f of x equals 2 to the x and g of x equals log base 2 to the x. Now, f of x equals 2 to the x, that's the same function that we graphed in our previous lesson. So we'll make a quick table of values. When I plug in x equals 0, we get 1, x equals 1, we get 2, 2 squared is 4. 2 to the negative 1 power is 1/2, and 2 to the negative 2 is 1/4. So when I'm trying to make my table of values for g of x, which is the inverse, I'm just going to switch those two columns. My x values now become 1/4, 1/2, 1, 2, and 4. And my y column becomes -2, -1, 0, 1, and 2. Okay, and that note just says from one table to the next, we're just switching those x and y values. So we'll graph f of x in white. We have 0, 1, 1, 2, 2, 4, -1, 1/2, -2, 1/4. And we know we've got a horizontal asymptote here at 0. Now in red, I'll graph g of x, which is the inverse. So we have a point, I'm going to start with the easy ones, 1, 0, 2, 1, and 4, 2. And also over 1/2 down -1, so 1/2 -1 and 1/4 -2. And when you look at that graph, if you consider the line y equals x, which let me use a different color for that. The line y equals x is right here. If you take and turn your page so that dashed line is vertical, you can see a very clear reflection about that line from my first graph to my second. Since we saw in our first video on exponential functions, finding the table of values for an exponential function is very easy. We can just plug values into our calculator. Now when we want to graph our log function, we're just going to switch those x and y values. So here we're going to talk about the characteristics of your parent function, log base b of x. Just like when we were talking about the characteristics of our parent function for exponentials, b can hold many different values, and we'll talk about the difference between what the graph looks like based on the value of b. But in general, the other characteristics remain the same regardless of what b is. So the domain of your log function, thinking about my exponential functions, and actually I'm going to give you a second, turn back in your notes and find this same slide when we were looking at exponential functions. Okay? So take a second, find that. We're looking for this same slide, but when it said y equals b to the x. And while you're looking for that, remember the properties of inverse functions. That's what we're dealing with here, inverses. The domain of a function is equal to what? The range of its inverse. So if I'm trying to find the domain of a log function, that's the same as the range of its inverse, y equals b to the x. And from that table, what was the range of your exponential function? The range was from 0 to positive infinity. So that's now the domain of our log function. The range of a function is equal to the domain of its inverse. Since the inverse of a log function is the exponential, the range of my log function is equal to the domain of that exponential function, which is, whoops. Sorry, we got out of whack. There we go. The range is going to be from negative infinity to positive infinity. What points are all of my log functions going to pass through? Look at that ordered pair that all exponential functions pass through. All of our exponential functions pass through the point 0, 1. So all of our log functions are going to pass through the point 1, 0. And again, this is not accounting for any type of horizontal shift or vertical shift or reflection or any other transformation for that matter. Okay, this is just our parent function. Our log function, our parent function, has no y-intercept. And that just means that we've got a vertical asymptote instead of a horizontal asymptote, a vertical asymptote at x equals 0. If the base of your logarithm is greater than 1, then your function is monotone increasing. And that's going to look like the picture we just had, like that. And if the base is between 0 and 1, then the graph is decreasing. Which will look like this. And this last bullet here is actually for what we listed up here, that we have a vertical asymptote, so we don't need to rewrite that. The vertical asymptote is related to the fact that there is no y-intercept. So let's talk about finding the domain of our log function. Thinking back to that lesson on our library of functions, we talked about how when I looked at the domain of a square root function and we saw that the domain was restricted for the parent function, that meant that the domain of any square root function was going to be restricted. Well, if you look back at your previous slide, the domain for our log function was restricted. It was restricted from 0 to positive infinity, not including 0. So what does that mean? That means that the argument, whatever we're taking the logarithm of, must be positive. So in this first equation, y equals log base 2 of x minus 3, we're taking the logarithm of x minus 3, not just x, but x minus 3. So that value, that expression must be positive, which is strictly greater than 0, and I can solve this to find the domain. Adding 3 to both sides, we get x is greater than 3. And if I set up a number line just to see what my interval is going to be, x is greater than 3 means I shade to the right. And I'm not including 3, so I'm using a parenthesis. So the domain of this function is 3 to positive infinity. This is very similar to finding the domain of a square root function. The difference here is that with a log function, it has to be strictly positive. It's not just non-negative. G of x equals log base 3 of x plus 2. Again, my argument, whatever I'm taking the logarithm of, must be positive. So here I'm going to subtract 2. X must be greater than negative 2. And again, setting up our number line, we've seen that using the number line really helps us set up our interval because we can visually see where it starts and where it ends. I reviewed with you guys just recently, an interval must be stated from least to greatest. So make sure that you're setting up your intervals correctly. Otherwise, they're going to be continued to be marked wrong. X is greater than -2 is values to the right. We're not including -2. So our domain is -2 to positive infinity. So we've looked at graphing exponential functions. We've looked at graphing logarithmic functions very basically, but now we want to think about how transformations play a role in graphing a log function. Again, I've mentioned this very, very quickly in a few minutes ago, but we can't use our calculators to make a table of values. So we're going to have to utilize the fact that logarithmic functions are inverses to exponentials if we want to graph them. So to graph the transformation of a log, we're going to start by finding the inverse of that function. If we're starting with a log, what type of function is our inverse going to be? It's going to be an exponential function. We can use our calculator then to create a table of values for any exponential function. And then once we have a table of values for our exponential function, we're just going to flip those x and y values to graph our inverse, or to find the inverse, which is our log function. So here's an example. G of x equals log base 3 of x plus 2. How do we find the inverse of this function? Our first step is to switch x and y. So this becomes x log base 3 of y plus 2. And now I want to solve for y. From here, if I want to get rid of this logarithm, I want to convert to exponential. Again, that idea that the inverses undo each other, if I need to undo a logarithm, I'm going to have to use exponential. So this becomes 3 to the x equals y plus 2. And now to solve for y, we subtract 2. So y, which is our inverse, is equal to 3 to the x minus 2. And this is an exponential function. We can use our calculator to evaluate our outputs for given inputs. I'm just going to rewrite our functions up here. We just found our inverse. It was 3 to the x minus 2. And our original function was log base 3 of x plus 2. All right, so we're going to create a table of values for G inverse. And I'm trying to be specific with that y column when I name it, just so that it's not confusing when I go to plot points on my graph. For an exponential, my domain is all real numbers, so let's use -2, -1, 0, 1, and 2. And for these points, I will allow you to use a decimal. When we're finished, I'll talk about what you want to do for your homework online. But for right now, we're going to just approximate these using a decimal. Some of them won't be. When we plug in x equals 0, we get 3 to the 0 is 1. 1 minus 2 is -1. Plug in x equals 1. 3 minus 2 is +1. 3 squared is 9. 9 minus 2 is 7. And these values are the ones that we're going to have decimals, because when we have a negative exponent, that's when we get a fraction. 3 to the -1 is 1/3 minus 2 is -1.66 approximately. And 3 to the -2 is 1/9 minus 2 is approximately -1.88. So next to this, now that we have our table of values for the inverse, we're going to set up the table of values for g of x, which is our log. And all we're going to do is switch our columns. So we've got x values of -1.88, negative 1.66, negative 1, 1, and 7. And our y values are negative 2, negative 1, 0, 1, and 2. Now the question only asks us to graph our inverse, so this is the one that we're going to graph. We're not going to bother plotting these points. We only found this first table of values so that we could find the ordered pairs for our graph of g of x. So again, I like to start with my easy points. Negative 1, 0, 1, 1, 7, 2, which kind of ran out of room, but it's down here. You can still see it a little bit. I know I'm almost off the screen there, but you guys can see where the graph or where the 0.72 is. Now I have a point at negative 1.66, negative 1. So I'm going to have to approximate that. Negative 1.66 is about negative 1.5. So maybe put my point right there at negative 1/2, negative 1. And then negative 1.88 is even closer to negative 2, but not quite there. And we're at negative 2. Now, something else we can do, which is going to help us finish this graph, is to find the domain of g of x. The domain of g of x, which again is log base 3 of x plus 2, is going to be found by finding where x plus 2 is greater than 0, just like we did in those previous examples. So x must be greater than negative 2, which actually identifies where the vertical asymptote is. Our vertical asymptote is going to be at negative 2. By placing that vertical asymptote, we can make sure that when we connect the points that we don't cross over it. So there's the graph of g of x. If you choose to graph both g of x and its inverse on one grid, you need to make sure that you label both of them, okay? Don't just leave two graphs and call it a day. Tell me which one is the original function g of x, which one is its inverse. And you can do that quickly by just labeling one g of x and the other one g inverse of x. Oh, so let's go back to, I was going to mention what you need to do for the homework. When you're plotting points online, you do have the option of plotting an ordered pair and exact ordered pair. So instead of using negative 2, negative 1.88, what I want you to do for this point, well, actually not that point. Let's see if I can, nope, oh well. For plotting this point, I want you to type in what that negative 1.88 actually was. If you look over here from that first table, that was 3 to the negative 2 minus 2. You can actually type that in as a x value, and then your y value is negative 2. Now you could simplify 3 to the negative 2 and write it as 1/9 minus 2. And if you really wanted to combine those two fractions, you could do that too. But what's really nice about that tool to just plot an ordered pair, it will plot any version of that. So even this first one, when you just plug in the negative 2 for x, it will work to plot the point exactly where it needs to go. But you are going to get marked off if your points are approximations. Okay, so don't use a rounded decimal when you're using that plot point tool. So we've been talking about our calculators and how our calculators are just not worthwhile when it comes to logarithms. And that's not really true. Our calculators can evaluate logarithms that have a base of 10 or a base of e. Log base 10 of x, we actually just write log of x. Similar to when we're talking about a square root, you know how we don't use an index. So if I've got the square root of 2, I don't put that little 2 as the index. It's just understood that that is the index. Same thing here. When we just have log of x, it's understood that the base is 10. Log base e of x, when you've got that natural number as our base, it's actually called the natural log of x, written ln of x. Now I have these two pictures here. One is okay, the pink calculator's all right. The one on the right is not fantastic, but I want you guys to get your calculator out, whatever calculator you plan to use on the exam. Remember that you're only allowed a scientific calculator, which you're going to need. A basic calculator will not have these tools. They won't have these buttons. So get your calculator out, and I want you to find the two buttons that say log and ln. If you're looking at this pink one right here, it looks like ln and log are right below the second key. If you're looking at the calculator, that's all, well, you can't really see me pointing, but the one on the right, they're right next to the off button. Your ln and your log button are on the off button. Now, these are just two very common scientific calculators. That's why I chose these images. But make sure on your calculator that you can find those two buttons. Also, you want to make sure that you know how to use those two buttons. Depending on the operating system for the calculator, the syntax, the order in which you type stuff in is going to change. So if you're having any issues getting an answer using your calculator, make sure you bring it to class so that we can talk about it and look at your calculator specifically. So let's look at an application, and this problem we'll actually get a chance to use our calculator. The percent of adult height reached by a boy that is X years old can be modeled by the function f of x equals 29 plus 48.8 log of x plus 1. I'm not sure what this is right here. I can't seem to move it. Nope, I can't move it. Sorry. So ignore it. I hope it's not on your copies, but there's some little box here. But this should just say 48.8 log of x plus 1. What percent of his adult height is a boy that is 11 years old? So 11 gives us our x, right? We're talking about a boy that is x years old. So we're trying to find f of 11. When you substitute in 11, we get 29 plus 48.8 log of 11 plus 1. Simplifying this, we know that this is equal to 12. And now we can type this into our calculator. You might want to evaluate it piece by piece, starting from the inside. So we would find log of 12 and then multiply by 48.8 and then add 29. Depending on your calculator, you might be able to just type the entire expression in, hit equals, and it'll give you the right value. But we should get an answer of 81.664. And the function gives the percent, so that's why I have my unit as a percent. Please make sure that you guys are able to get this answer using your calculator. With our log functions and our natural log functions, the syntax is really important, and I want to make sure that you guys are comfortable using that before you show up for the exam. So let's talk some more about finding the domain. Did I miss a slide? Nope. But I did sort of. Okay, I'm going to add something in here. I guess I missed a slide. I want to talk a little bit more about the natural log. The natural log is when we have a base of e. And we just mentioned that before. So our natural log, log base e of x, we actually write it as just ln of x. Now, e is still just a number. It's 2.71828. So it's like saying log of base 2.71828. And since it's still just a log function, we have the same rules, especially when it comes to domain. So when we're trying to find the domain of a log function that uses natural log, we use that same principle that our argument must be positive. So for this example, 4 minus x must be greater than 0. Now we can either subtract 4 or add x to both sides. I like to add x because then I don't have a negative on x, and then I don't have to remember to flip the inequality symbol. So we have 4 is greater than x, and I can rewrite this as x is less than 4. So when I'm looking at x values less than 4, they are to the left of 4, and x cannot equal 4. So my domain in interval notation begins at negative infinity and ends at positive 4. Find the domain of f of x equals natural log of x squared. The argument must be positive, so x squared must be greater than 0. When we try to solve for x, we take the square root of both sides. So what happens when we take the square root of x squared? I'm actually teaching this in my intermediate classes. When the index and the exponent match, they cancel each other out. Those are inverses also. But when that index is even, because this is referring to just the positive principal root, we must actually talk about the absolute value. We have to include the absolute value of x. They don't just cancel each other out. So this is saying that the absolute value of x is greater than 0. Now, absolute value is talking about distance. So if I'm setting up a number line, here's 0. What values have a distance from 0 that is greater than 0? Well, that's all of these values. They all have an absolute value greater than 0. Same with all of my negative values. The only value whose distance is not more than 0 from 0 is, in fact, 0. So this domain is from negative infinity to 0, union 0 to positive infinity. Now this rule, when we take the square root of something squared, include absolute value, that's a rule that's oftentimes forgotten, and that's okay. We can also think about this just in terms of number sense. If I want to figure out where x squared is greater than 0, think about what values you can plug in for x and square them and get something positive. If I square a positive number like 1, 2, 3, 4, so on and so forth, well, x squared is going to be greater than 0. If I square a negative, though, it's also going to be a positive. So what one value, when you square it, is not greater than 0, that is in fact 0. X cannot equal 0 in this inequality. That's the only value it can't be. So then again, we set up our number line. Here's our value of 0 with our open circle, and we're talking about everything to the right and everything to the left. So you do have two options of thinking about that, and just depending on how you perceive the problem, you're going to think about it differently. So let's just review some properties of logarithms, and then our next lesson is actually going to be looking at some more properties of logarithms. I've listed my properties both using log with a base b and also as natural log. I don't want you guys thinking of them as two separate sets of properties, but a lot of times students do. So hopefully seeing them side by side, you'll start seeing that they are the exact same properties, but when we have the natural log, it's just like having log base e. So instead of having a b, it's an e. Log base b of 1. To evaluate this, b to what power is equal to 1? That's how we evaluate a logarithm. Well, any base raised to a power of 0 is 1. B to what power is equal to b? B to the first power is equal to b. Over here, the natural log of 1. Now we have a base. You can add it if it makes you happy, a little base of e. And now we're trying to figure out e to what power equals 1. Well, e to a power of 0 is equal to 1. So notice the similarity between these two, this one and this one. It's the exact same rule. This one is using a base other than e, and this is using a base of e. The natural log of e, again, if you envision an imaginary e right there, an invisible e, not imaginary. E to what power is e? E to the first power is itself e. Log base b of b to the x. This is our inverse property that we proved earlier. This is equal to x. Same with b to the log base b of x. Another inverse property, so it is equal to x. seeing these inverse properties using a natural log. Again, natural log just has a base of e that we don't write. It's just understood to be there. So the natural log of e, base e of e to the x is x. And e raised to the natural log of x, if you envision that little base of e, you can see how it's the exact same rule that we have over here. And this is also equal to x. These properties are going to become very important in our next section because we're going to start simplifying expressions that are involving logs and exponential terms. So we want to make sure that we know these really well. So again, putting all this together, we looked at graphing logarithmic functions today and all their properties. We're going to focus on the relationship between exponential and logarithms to graph log functions. The relationship is that they are inverses. If you're still kind of shaky on this, or maybe you don't remember a lot about inverse functions, I encourage you to maybe go back and rewatch that video that dealt with inverse functions. That way you understand exactly what we're talking about when we're switching our x's and y's and we're referring to the domain of an inverse equaling the range of our function. So take a look at that video if you want a refresher, and we'll see you guys next time to review some more or learn some more properties about logarithms.